Precalc notes 10.1, sequences, series, and sigma notation. So a sequence is an ordered list of numbers. And then a term is each number in the sequence. A finite sequence has a finite number of terms. Finite number of terms. So that means it stops, right? It doesn't go on forever. There's 10 terms or 12 terms or something. Infinite, though, those are going to have an infinite number of terms. So they do go on forever. An explicit formula gives the nth term, a sub n. So the terms are going to be like a sub 1, a sub 2, a sub 3 as a function of n. So basically explicit means there is a formula. So if I want to know the 10th term, I can find exactly that one. I don't have to find all the other ones in order to get the 10th one. So for 1, we are looking at just some basic sequence stuff. So we want to find the next 4 terms of the sequence. So we're always looking for what is the pattern here. So from 3 to -1, what's going on? Am I adding, am I subtracting, multiplying, or dividing? And we're really mostly in the next section going to be looking at adding and subtracting. 3 to -1, so that means I'm subtracting 4, and then again I'm subtracting 4, and again I'm subtracting 4. So the pattern is subtract 4. And once I figure that out, I can do the next couple terms. So then I'm going to have a -13, -17, -21, and -25. All right, for the next one, it looks like down 3, and then 5, and then 7. Okay, so we're going down by odd. So next I would subtract 9, and then I would subtract 11, and then I would subtract 13, and then I would subtract 15. I guess I better go back and put my commas in there. So notice on the first one, I didn't keep writing -4 because I could just do that in my head. But on this one, I kept writing down those numbers I was subtracting just to kind of help. So for this one, we were subtracting consecutive odd numbers starting with 3. And I'm sorry that's so messy. So we're subtracting consecutive odd numbers starting with 3. So now they're giving us an actual formula, an explicit formula, and they're saying find the first 4 terms. So a sub 1, I'll get by putting a 1 in. So that's 1 to the 3rd power plus 1. 1 plus 1, a sub 1 equals 2. A sub 2 is going to be 2 cubed plus 1. 8 plus 1, which is 9. A sub 3 is 3 cubed plus 1. Let's see. 27 plus 1 is 28. Not quite enough room for a sub 4. 4 cubed plus 1 is 64 plus 1 is 65. So then I do want to list them out like I would for a sequence. So I'm going to write 2, 9, 28, 64. Or sorry, 65. So those are my first 4 terms of the sequence. So a recursive formula gives one or more of the first few terms and defines each new term using previous ones. So we don't have a formula to find, say, the 20th term. If I want the 20th term, I need to use this recursive formula and keep going until I get to the 20th term. So then we want to find the fourth term of this recursively defined sequence. So this is kind of what those ones look like. So they give me A1 and then they say A sub n, but here instead of just A sub n, I have A sub n minus 1. That's the term before. That's A sub n minus 1 is the term that's one before that term. So I'm always looking at the previous term to be able to figure out what's going on. So if I want to find the fourth term, first I have to find A2. And that's going to be 3 times A sub 2 minus 1 minus n, which is 2 plus 2. So again, this is 3 times A sub 1. We're showing a lot of work on this first one. These are just going to make a 0, so I don't have to worry about those. And then 3 times A sub 1 would be 3 times 3. So A sub 2 is 9. Now, if I want to find A sub 3, that means I do 3 times A sub 2 minus 3 plus 2. So that's going to be 3 times 9 minus 3 plus 2. So 27 minus 3 plus 2, or 26. Okay, A sub 4 now, the one I actually want. Now I do 3 times A sub 3 minus 4 plus 2. So let's see, 3 times 26 minus 4 plus 2. I guess I could just really make that a minus 2. Let's see, 60, and 3 times 6 is 18. So wouldn't that be a 78 minus 4 plus 2, or just a 76? So the fourth term is 76. So this is really just kind of all about these sequences and series today. So far we're just looking at sequences. Fibonacci sequence, we're not going to do this example, but I do want to go over what a Fibonacci sequence is. It is a famous recursive sequence. I really wish we could watch some videos on it. You should absolutely search on YouTube for Fibonacci sequence. You will not be disappointed. And it's found in nature. And it starts out 1, 1, 2, 3, 5. So what you do is, like 2 is when I add 1 and 2 together. 3 I get by adding 1 and 2 together. 5 I get by adding 2 and 3 together. So now 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. So I add those previous two terms. And it's one of those cool patterns that just keeps coming up in nature. And so you should definitely, so the example we had was about branches and the way they were growing and how many were growing at a time and how many there were total. So it is really cool, and I wish we had more time to explore that this year. So now we're going to look at whether sequences converge or diverge. So converge is if an infinite sequence has a limit. If an infinite sequence has a limit, it converges. And then diverge would be when an infinite sequence has no limit. So this means if I keep finding terms, like I find the 100th term, the 101 term, the 102 term, converge would be like they just get closer and closer to that same number. They're all at like 1 or something. So converge makes me think about when we did graphing before, and say we were graphing like an inverse variation kind of thing. And what if we have a dotted line here at y equals 1, and we're graphing this side, and we're graphing this side, and as I get closer and closer, as x goes to infinity, then I get closer, my y gets closer and closer to 1. So it's kind of that kind of thing. So that's a picture of what we're looking at. So the difference is, of course, we're looking at lists of numbers. We're not looking at a graph. They're similar, but they're not really the same thing. But but it gives you kind of an idea of what's going on. So now I want to determine whether or not they're going to be divergent. So I want to think about what happens as n grows. As n grows, that 1/4, the 1 is going to stay 1, right? 1 to the nth power is still going to be 1. The denominator grows. And negative 1/4 to the nth power gets smaller and smaller. And is going to get closer to 0. Even think about if I made that just like the fourth term, right? Then that would be negative 1/256. I guess it'd be positive 1/256, but 1/256 is a really small number, and that's just the fourth power. So as it gets smaller and smaller and smaller, it's going to get closer to 0. And because of this minus sign and this minus sign over here, it's going to bounce. It'll be like below the 0, above the 0, but it's going to get closer and closer to 0. So that's kind of our prediction. And then if we just find, let's say we found A5 or A6, just for fun. So A5 would be negative 4,000 times negative 1/4 to the 5th power. So then I would have to do, let's see, it's going to end up being negative, right? Oh, no, it'll end up being positive. A positive. So let's do 1/5. Sorry, I'm grabbing my calculator out here. I was not going to show this example, and then it occurred to me I really should. So 1 divided by, and then I'm going to do 4 to the 5th power. And then I'm going to multiply by 4,000. And I get 3.90625. Okay, and then if I look at like A sub 6, 4,000 times a negative 1/4 to the 6th power. I did not leave myself much space here, but I did upload my notes that look far neater than this. And then I have, let's see, this one's going to be an odd this time. So 4,000 times 1/4 to the 6th. This is going to be negative 0.976525. So they are getting smaller and smaller and smaller. Whereas if I would look at just like 1/4 to the 1st power times 4,000, I would get 1,000. So you can look at those. You can look at those terms, at the bigger number terms. And we're only looking at 5 and 6. I mean, if we're talking about as this goes to infinity, like we could be looking at the 100th term, right? Okay, so on the second one, and we're not going to do a third one, we're just going to do 2 here because I am running out of space and these are a little more time consuming, and that's what I'm going to do in class. So this time, as n grows larger, as n grows larger, so let's think about this. So negative 2 is going to get a bigger, go to a higher and higher power, so the numerator is going to get larger. Numerator is bigger, okay. And the fraction, it's not going to converge on anything, is it? And let's say we'll diverge because it's just going to keep getting bigger and bigger and bigger. So if I find like A sub 1 on this one, we'll start out with A sub 1 this time. I'd have negative 2 to the 1st power over 2. Negative 2 over 2 is just negative 1. If I look at A sub 2, negative 2 squared over 2, 4 divided by 2 is just 2. So if we can already see, like, it's not getting bigger, it's getting smaller this time. A sub 3 would be negative 2 to the 3rd over 2, or negative 8 divided by 2 is now a negative 4. So we're switching back and forth between negative and positive, but the absolute value is growing. Negative 2 to the 4th would be a 16 over 2, so a to the 4th is 8. So it's just going to keep getting bigger. We're looking at divergent. So divergent on this one we needed to say convergent. So these are going to be important words next year. All right, so on to the next thing. So now we're looking at series instead. So a series is when you take your sequence and you add them all up instead. So this is the indicated sum. Lots of stuff today. Of all the terms of a sequence. An infinite series, oh, I forgot the word series in here. So series is the indicated sum, but if it's finite, it's of a finite sequence. So I needed to have the word finite in there. So infinite is going to be the sum of terms of an infinite sequence. Sum of terms of infinite sequence, which might be weird, right? How can we add something up if it's infinite? So the issue is that sometimes we can't. If we have a divergent series and it keeps getting bigger and bigger and bigger, then you're right, we absolutely cannot add them all up. But what if, like on that last one, it converges to 0? If it converges to 0, then we really can be able to add all those up, because at the end of it, it's just going to be 0 anyway. So we can only find if it converges. And then partial sums are when we just add the first n terms. The sum of the first n terms of a series, and then we would call that S sub n. So sum of those first n terms. So for a partial sum, you might find the sum of the first 10 terms or the first 20 terms. So if I want to find, in example 5, in this first part, and we're not going to do the second part because, again, we're looking at time here, and I did not actually do these in my notes that I put online anyway. If I want the fifth partial sum, that means I need to add the first 5 terms. That's what we're doing. So I find A1. A1 would be 1 squared minus 3. Let's see, 1 minus 3 is negative 2. Then I find A sub 2. A sub 2 is 2 squared minus 3. 4 minus 3 is 1. A sub 3 is 3 squared minus 3. 9 minus 3 is 6. A4, 4 squared minus 3. 16 minus 3 is 13. And we're going to squeeze A5 in. 5 squared minus 3. 25 minus 3 is 22. So now those are the ones I want to add together. So if I'm finding S sub 5, the sum of the first 5 terms, I'm going to add negative 2 and 1 and 6 and 13 and 22. And that's going to be 40. So S sub 5, the sum of the first 5 terms is 40. So series is just, now I am adding my sequence together. So we have a notation to show this. We have a special notation that says add a bunch of stuff together, and that is sigma notation. It is sigma, is this Greek letter. Sigma for Greek letter. And the letter looks kind of like a giant E, but sharper and pointier. I know you've seen it before. It's also called summation notation. And that's because we're adding a bunch of things together, right? We're summing. Summation notation. So both of these are commonly used words in textbooks. So I just want to make sure you get to see both of them. And so when I have the sigma notation at the bottom of it, it's going to start with a number like, say, n equals 1 or n equals 0. And this is called my lower bound. So this is what I start with. And it starts with you start with the given number here. Start with this number. This number. And then there's going to be something on top. We're just going to write K for now. And this is the number you're going to end with. End with this. and it is your upper bound. So we're kind of talking about nuts and bolts and vocabulary. So we have a lower bound that we start with, we have an upper bound that we end with, and then we have this little formula thing here. This is the formula that we substitute into. And so basically when I see something like this, I find a sub 1, and then I add a sub 2, and then I add a sub 3, and I keep going until I get to a sub k, because that's my upper bound, and that's when I'm done. So whatever this is, I have to keep putting 1 and 2 and 3. I keep substituting numbers in, and then because it's summation notation or sigma notation, I'm adding all of those terms together, and I stop with my upper bound. So we're just going to do some easy ones here. And then this is it, actually. And we're just going to do 2. And I know that's because of time and because of space. I had saved these and then changed my notes a whole bunch, and now I don't have Smartboard anymore, so I can't actually change them on here. But I know that in class we're just doing an A and we're doing a B, so we're going to skip that other one. So this is just so that my notes are going to match what I upload later. So what this means is I need to start with 1. So if I substitute 1, I'm going to have 1 squared minus 1. And that's going to be my first term. This is going to be my a sub 1. And then I need to add, and I'm going to substitute in 2 now. So I'll have 2 squared minus 2. And that's going to be my a sub 2. And then I'm going to add, and then I will have 3. 3 squared minus 3. And that's going to be my a sub 3. And then my last term, my a sub 4 term, would be 4 squared minus 4. And I know to stop at 4 because it says start at 1. My lower bound is 1. My upper bound is 4. So now I just have to go through and simplify these. Well, this would be a 1 minus 1 and a 4 minus 2, 9 minus 3, and 16 minus 4. So let's see. 0 plus 2 plus 6 plus 12. And so our sum is 20. So that's kind of what we're looking at here. So this next one goes to infinity, and that's why I wanted to do this one, just so you can get an idea of what's going on here. So I can agree that this must converge, because as my denominator, I have 10 to the nth power my denominator. That's going to get closer and closer to 0. The whole thing's going to get closer to 0. So I know that it is going to converge, so I should be able to find this. So if I am doing to infinity, that means like maybe I do 4 of them and I just write dot, 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 and hopefully I'm finding a pattern. So this is going to be, if I do my first term, 3 times 1 over 10 to the first. My second term would be 3 times 1 10 over 10 squared. This is one where really you're going to see the method and then be able to do this on your homework. 3 times 1 over 10 to the fourth, and then plus dot, dot, dot. Okay, so this is 3 times 1/10. The next one would be 3 times 100. And the next one would be 3 times 1,000, or 1,000th, sorry about that. And then 3 times 10,000th, 1 over 10,000, or 10,000th. I don't know if I'm saying that clearly enough or not. So this first one as a decimal, well, let's just do 3/10 first, 3/100ths, 3,000ths, 3/10,000ths. So I think in decimal form you'll see it better though. So if I have 3/10, that's 0.3, that's my tenths place. 3/100ths would be 0.03, that's in my hundredths place. The next one would be 0.003. So hopefully you can kind of see where this is going. And then 10,000ths, so that would be 3 zeros and then a 3. So I think we can agree this is going to be 0. When I add them together, 3, 3, 3, 3. And that means it's going to equal 1/3. So we were able to just add together something that has an infinite number of terms, because we can tell that's going to just keep going. We're going to keep adding more 3s to that, and it's going to converge. The sum is going to be 1/3. So kind of cool. That is it for our 10-1 notes.